If you were to ask a math teacher what are some of the most important big ideas in algebra, certainly one of the ideas they would tell you is the idea of functions. Okay, functions can be used to describe many relationships in the real world, and they're one of the primary ways that we use math to model situations in the real world. We're going to start this lesson by looking at some examples of functions. And here's one. The amount of the bill you pay for internet data usage on your cell phone depends on the number of gigabytes of data you use. The way in which the usage determines the bill is described in the data plan. In this example, the way in which one numerical quantity depends on another is described verbally. The graph and table of data show NASDAQ Composite Index from January 2011 through January 2017. The NASDAQ index is a statistical measure of how well a portion of the market is performing. The index tracks approximately 4,000 stocks that are traded on the National Association of Securities Dealers Automated Quotations, NASDAQ, System Electronic Stock Exchange. The graph and table display the index value corresponding to each year. In this example, the way in which one quantity corresponds to another is described graphically and numerically. Suppose a rock is dropped straight down from a high point. From physics, we know the distance traveled by the rock in t seconds is 16 t squared feet. So the distance depends on the time, and this relationship is described by an algebraic formula. These three examples share some features. First, each involves two sets of numbers, which we can think of as inputs and outputs. Second, in each case, there is a rule by which each input determines an output. Each of these examples may be mentally represented by an idealized calculator that has a single operation key. A number is entered, input, the rule key is pushed, the rule, and an answer is displayed, the output. The formal definition of a function incorporates the same common features, input, rule, output, with a slight change in terminology. A function consists of a set of inputs called the domain, a set of outputs called the range, and a rule by which each input determines exactly one output. Another way to think of a function is as a vending machine. If you have, for instance, a Coke machine, there's an input, which is the button that you push, and an output, which is the drink that comes out of the machine. For every input, there's only one output. If you push the button that says Coke, you should only get a Coke. If you push the button that says Sprite, you should only get a Sprite. So for every input, there's only one output if the machine is functioning correctly. On the other hand, if there are two inputs that are the same, as a lot of machines have, for instance, two inputs for Coke, two buttons, each of those buttons will only give you a Coke, so there's still only one output for each input, even though two of the inputs can have the same output. This machine is still functioning properly, so it still models a function. In example 4, we're asked to find the domains and ranges for the functions in examples 1 and 2. So let's go back and take a look at example 1. I want to look first at these words depends on. These words help me understand basically what the output is and what the input is. The thing that depends on something else is the output. Okay, and the thing that is dependent on is the input. The thing that depends on something else is the output. And the thing that it depends on is the input. So in this problem, the amount of the bill would be the output or the range. And the number of gigabytes would be the input or the domain. In the second example, we could say that the NASDAQ index depends on the year that we're looking at. So the year would be the domain, and the actual index value would be the range. Please note that in this example, we show the typical arrangement where the domain is in the first column and also on the horizontal axis, and the range is in the second column and on the vertical axis. Pause the video now and work on checkpoint 1. Earlier, I said that there are many real-world situations that can be modeled with functions, but we need to be careful because not every situation can be modeled with a function. So we need to make sure that we have the qualities of two sets of numbers and the relationship between an input number and an output number. That every input has exactly one output. So we're going to look at a few situations which may or may not be functions. Okay, our first one says if I use the optical reader at the checkout counter of the grocery store to convert codes to prices, is that a function? So we've got codes to prices. Okay, we've got two sets of things here. Is it true that every code gives us a unique price? Only one price. Okay, if every code didn't give us the same price every time, then some people would pay more for something than others. So yes, this is a function. Okay, here's another situation. A loan officer at Bank of America asks each applicant to provide his or her social security number. So we've got an applicant and their social security number. Okay. Every applicant is going to have only one social security number. You can't have more than that. So yes, this is a function. Okay, the next one. Same thing, same situation. A loan officer asks each applicant to give a credit card number. Credit card number. So we've got the two quantities. is it only one response for each applicant? Some applicants are going to have more than one credit card, so they could give more than one response here. And there may even be some applicants that have no credit card, and then there would be no response. So this is not a function. Okay, let's do one more. If I put a number in the calculator, and then I press the x squared key, will I get one answer? I think we'd all be a little upset if we didn't. Every calculator, if I put a number in and I square it, there's only one answer. So this is also a function. But wait, there's more. I'm going to give you a table. In this table, does every input have exactly one output? I think it's fairly easy to see that that's not true, because here I've got 1 and 3, but here I have 1 and -3. Those are not the same. These two are the same, but these two again are not. So this is not a function. Okay, and then my last one. If I give you this equation, y equals 3x minus 5, will I get a unique y for every x that I put in? In other words, are there any two x's that I could put in here and get the same value for y? And the answer there is no. So this is a function. And you might recall from the last chapter that this is a linear equation, and therefore it is a linear function. Okay, and as we'll see later on, any linear equation, with one exception, is going to be a linear function. And that exception is for a vertical line. Okay, if I have the equation x equals a number, that's a vertical line, and it is not a function. Pause the video and work on checkpoint 2. In the last part of our last example, we looked at a linear equation. In a linear equation, we say that the equation defines y as a function of x because every x that we put in the equation gives us a unique y. We can't ever put an x in and get two different y's. So in this example, we'll be looking at some other functions and equations to see if they define y as a function of x. This is our first equation. Y equals negative 4x plus 11. In this equation, just like the last one, we've got a linear equation, and every x that I put in here is going to give me one and only one y. So, is this defining y as a function of x? And the answer is yes. Let's look at a different equation. Y squared equals x. Okay, in this case, let's say I let x be 36. If x is 36, I have two possible values for y. Y could be 6 or y could be negative 6. So this is not a function. Okay, as I said before, if I've got a linear equation, every linear equation that doesn't define a vertical line is going to be a function. In this equation, this y squared is kind of should set off a little alarm in your head. If I have y squared in an equation, I'm not likely to have a function. So that's just kind of a red flag. Say, nope, that's not going to be a function. Pause your video now and work on checkpoint number 4. Another thing we're concerned with function is finding the domain. So we're going to look at some functions that we know are functions and determine what the domain is. So here's the first one. Y equals x to the 4th. What values can I assign to x that is going to make y defined? And the answer is any value that I assign to x will make y defined. So we say that the domain would be, we can draw the R this way with 2 bars. It stands for all real numbers. If you're asked to write this in interval notation, it would look like this. Okay. Here's another equation. We know when we have a square root equation that the stuff inside the square root has got to be either positive or 0. If this is negative, then we end up with imaginary numbers, which is not part of a function. So let's say that x minus 6 has to be greater than or equal to 0, which means that x has to be greater than or equal to 6. So for this, I could write just this much for the domain, or again in interval notation, but we could start with 6. And since 6 is allowed to be part of the domain, we use a square bracket, so 6 to infinity. Always use parentheses with infinity. And this is the domain for that function. How about if we switch it around a little bit and have 4 minus x? We still have the same here. 4 minus x has to be greater than or equal to 0. And now we're going to move the x over, so we'll have 4 greater than or equal to x, or we say x less than or equal to 4. So interval notation would look like this, from negative infinity to 4. Wait, there's more. How about this? Y equals the cube root of 4 minus x. When I'm working with a cube root, I need to remember that with a cube root, I can take the cube root of a negative number. So my domain is not limited like it is with a square root. So for this one, x could be anything. So I could again use the double bar r for all real numbers. I could go from negative infinity to positive infinity. Okay, let's look at another kind of function. We've done some square root functions. Let's do a rational function. Okay, in this function, my main concern is that I cannot let this denominator equal 0. So I'm going to write that denominator out separately. X plus 3 cannot equal 0. And then I can work this just like an equation. And I get x cannot be negative 3. So for interval notation, I would start at negative infinity and go up to negative 3 and use parentheses because I cannot have negative 3 as part of my domain. And then union, and another part would be from negative 3 to positive infinity. So this domain tells me I can use any number except negative 3. Okay, let's look at another one. This one's got kind of the combination of things. I've got a square root in the numerator. And a quadratic function in the denominator that I could factor. So let's do that. I can factor that into x minus 1 and x minus 2. So now my numerator tells me that x must be greater than or equal to 0. So that's part of my domain. I've got to be positive numbers. My denominator tells me that x cannot be 1 or 2. So now when I write my interval notation, I'm going to have 3 parts for it. The first part is going to tell me that x has to be bigger than 0 or equal to. So I start with a square bracket and go from 0. But when I get to 1, I have to stop there. So 1 and then a union. And then I start the next part at 1 and it can go to 2. And I have to stop there as well. And then my third part goes from 2 to infinity. So I've got 3 separate requirements, and I end up with 3 separate parts to my domain. Pause your video now and work on checkpoint 3. Pause your video now and work on checkpoint 4. When you first started out in algebra, we usually wrote an equation like this. Y equals, let's say, 3x minus 4. But there's another way to write functions, and it's called function notation. And for function notation, we simply replace the y with f of x. So this equation would be f of x equals 3x minus 4. and we read this f of x. This is not f times x, it's f of x. And although we usually use f, there's no magical power in f. We can use another letter if we prefer, and often we do prefer to use a letter that reminds us what the function is about. For instance, if we're working with a cost function and a revenue function, we might call them c of x and r of x. Okay, so let's look at writing some function notation. Here's an equation in function notation. Okay, and I'm asked to find 4 different things related to this function. The first one is g of -2. When I have something written in function notation and I'm asked to find a value for a particular value of x, all I have to do is replace every x with this number. So this is going to be -2 squared plus 4 times -2 minus 5. Well, -2 squared is going to be +4, but then I've got a negative out here. So I've got -4. This is -8, so a total of -12. And -5 gives me -17. Okay. The expression inside the parentheses doesn't have to be a number. We can also use another variable expression like this. I have g of x plus h. Again, I'm just going to replace the x up here with x plus h every time it occurs. So I start with negative x plus h squared plus 4 times x plus h minus 5. Okay, now I'm going to multiply this out, simplify it. And so here I'm going to have negative x squared plus 2xh plus h squared plus 4x plus 4h minus 5. Now I want to distribute this negative sign. So that makes this negative x squared, and this is negative 2xh, and this is negative h squared. Okay, so I've got this big long polynomial now with 2 different variables. We're going to take this a step further now and do g of x plus h minus g of x. So I'm just going to take my answer from the last part, negative x squared minus 2xh minus h squared plus 4x plus 4h minus 5. And now I'm going to subtract the terms of g of x. Well, if I subtract negative x squared, that's going to be plus x squared. And if I subtract 4x, that'll be minus 4x. And if I subtract negative 5, that's going to be plus 5. And you might have noticed that I wrote those terms under like terms. And they're all going to cancel out. And so my final answer is going to be, I'm going to rearrange this a little bit and put the powers of h in descending order. So negative h squared plus 4h minus 2x h. That would be my answer. Okay, we've got one more thing that we're going to do with this. Now we're going to take g of x plus h minus g of x divided by h, and we're going to make the assumption that h does not equal 0 so that we can divide by it. So I'm just going to copy this result. I've got negative h squared plus 4h minus 2x h, all divided by h. And every one of these terms has an h in it, so I can divide by h and just cross out one h in each term. So I'm going to cross that out and cross that out. This is going to become just h instead of h squared. So my final answer here is negative h plus 4 minus 2x. Okay, and this expression has a special name. It is called the difference quotient. And this is something that you will use later on in your more advanced courses on up into calculus. Pause your video now and work on checkpoint 5. Sometimes a real-world situation requires that we have more than one function to describe it, because as conditions change, the relationship between x and y changes. This is called a piecewise defined function. And we'll look at a piecewise defined function as it applies to the income tax laws. So I have a function, and this is for the state income tax in Connecticut for a single person with a taxable income less than $50,000. When I write a piecewise defined function, I always start with a curly brace, and I'm not going to end with a curly brace. I just leave it open. And there's two parts for each piece. Here's the first part, 0.03x. That's the function rule. But now I have to tell you, when does that function rule apply? And in this case, it applies if x is less than or equal to $10,000. Okay, so if your income is $10,000 or less, this is how you figure your tax. Now, what if your income is more than that? Now I have a different rule. And in words, basically this function says, if you make $10,000 or less, you can pay 3% tax. And now this rule, this is the 3% tax for the first $10,000. You would pay that. But then for income above $10,000, you have to pay 5% tax. Okay, so I have to write this if x is greater than 10,000 and less than or equal to 50,000. Okay, and I have to assume that if my income is greater than 50,000, I've got some other rule that's not described here. Okay, when we're working with a piecewise function, we first have to look at this part and decide which part of the function rule we need to apply. And then we look at the beginning part and apply the correct rule. So let's look at if I had an income of $9,200, how much tax do I need to pay? Well, looking at the rules, my X is less than $10,000. So I'm going to use this rule, which is 0.03 times 9,200, which gives me a tax of $276. Okay, in part B, what if my income was $30,000? Okay, again, I look at the rules first, and this is the rule that applies. I'm in between $10,000 and $50,000. So I'll be using this rule. So it's 300 plus 0.05 times X minus 10,000. Okay, and I know my X is 30,000, so 30,000 minus 10,000. I'll just write 20,000 in here. Okay, and 5% of 20,000 is going to be $1,000 plus the 300, so my total tax is $1,300 at this income level. Pause your video now and work on checkpoint 6. Let's look at another example of a real-life application for a function rule. In this problem it says, suppose the projected sales in thousands of dollars of a small company over the next 10 years are approximated by this function. So we're going to call this S of X because it represents sales. 0.07 x to the fourth minus 0.5 x cubed plus 2x squared plus 7x plus 62. Okay, and they tell us that x equals 0 is the current year. Okay, and so what are the projected sales for the current year? Well, if x equals 0, this is going to be 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 0, and all that's left is the 62. Okay, so S of X, I'll try it this way. S of 0 is 62. Now recall that they told us that this was in thousands of dollars. So the earnings projected would be $62,000. Okay, now let's look at sales in 4 years. So now we want S of 4. So I've got 0.07 times 4 to the fourth minus 0.5 times 4 cubed plus 2 times 4 squared plus 7 times 4 plus 62. Put all of that in your calculator, and you should come up with 136.72. This is S of 4, which gives us a sales figure. Remember, this is thousands of dollars, of $136,720. Pause the video now and work on checkpoint 7.